Okay. So I'm Lily, and today I'll be discussing the automation of scintillating tile scanning and a silicon photomultiplier characterization setup. Okay. So this summer, my project focused on light yield mapping with scintillating tiles and silicon photomultipliers. Many of these scintillating tiles, about 600,000 of them or so, are going to be used in the longitudinal board hadronic calorimeter, in the electron ion collider. And because so many tiles are going to be needed, it's of interest that these tiles all have uniform light yields, also just because of the energy resolution needs for the longitudinal board hadronic calorimeter. And in order to confirm this light yield mapping is done. Previously, this light yield mapping was done manually, just like moving the tile, but high precision is needed for this mapping. So in order to achieve that high precision, my project was focused on using a translation stage that could just do that all automatically up to precision of about 0.005 millimeters. So just some background, the electron ion collider is what it sounds like. You have a beam of electrons and then you have protons and heavy ions colliding, which you can see in this diagram. The blue is the electrons, green, and then the yellow is where the hadrons are coming in. So the electron ion collider is projected to be built in about 10 years or so at Brookhaven National Laboratory. And actually it will use some of the facilities that are currently in place, like the Hadron Ring. And very broadly, it will answer some questions of quantum thermodynamics, just how quarks and gluons interact. And generally, like if you see here, you can see the barrel of the electron ion collider, which has a lot of different detectors within it. And the detectors are broadly split into about 3 parts, which allow for high precision tracking of particles, particle identification, and calorimetry. And on the calorimetry front, there are actually 2 main types of calorimeters. There's the electromagnetic calorimeters and then the hadronic calorimeters. So with particle tracking, tracking detectors within the electron ion collider can only track charged particles because they use magnetic fields. So in order to track neutral particles, calorimetry is needed, which I'm going to talk about more in the next slide. And also the electron ion collider just has some requirements like very high luminosity and polarization. One cool thing that it can do that previous colliders haven't been able to do is detect exclusive events as well. So specifically, I was looking at the longitudinal board hadronic calorimeter, which is in the board or hadron going direction of the electron ion collider. So one thing is that electromagnetic showers only have one component. Because hadronic showers are composed of both an electromagnetic and a hadronic component, and they also typically go deeper and broader into detectors. So different technologies required for hadronic calorimetry relative to electromagnetic calorimetry, but still the same principle of calorimetry is there, which is that you want to capture energy and turn it into something tangible. So the LFH cal does this by using the scintillating tiles to whenever particles hit those, that's then turned into light, which I'm going to discuss more in the next slide. But in order to actually accurately do that, particles have to be fully stopped and absorbed. So this diagram is actually a little bit outdated because there still is tungsten in the design, which isn't currently true anymore. Right now, it's just steel absorption. But yeah, there are like plates of steel absorption there. And the LFH cal allows for particle flow measurements and reconstruction. Also, specifically for the LFH cal, because it's in a region of high pseudo-rapidity between like 1 and 3.5, it's a lot, or angular resolution and tracking momentum worsens a lot in that range. So high granularity is required, which is why about 600,000 scintillating tiles are needed. So the design of the scintillating tiles, they're these plastic injection molded tiles with a dimple within them. The previous design used wavelength shifting fiber, but those were really difficult to manufacture. So the design of that was switched to these. They also have an enhanced specular reflector foil, which just allows for all that light to be contained. And essentially what happens is any incoming particles hit this dimple, which is sitting on top of a silicon photomultiplier in the SIPM on tile method. And so when the tiles hit, that generates photons that are then read out by the SIPM. And then, so my methodology for this was essentially, we have a dark box in our lab right now that's 2 feet by 2 feet dimensions wise. And so I constructed that in AutoCAD, and then the translation stage would be placed in there and then be controlled through some software that could move that and do the scans. And also at the same time, take the same software could be used to actually collect the data from the scanning, which is essentially you have a strontium 90 source, which is emitting particles that hit your tile, generate photons read by the SIPM, and you also have a trigger tile below and above the actual scanning tile, which just makes sure all of the incoming radiation is from the strontium 90 source. Then that data would be analyzed. But in reality, what happened, the current box in the lab was too small. So actually, another student in our lab, Katie, she's going to talk about this in her presentation, but she designed a new box that's a lot larger. It's 2 feet by 3 feet by 4 feet. And you can see just like the different steps of the actual box construction here, which it is more difficult than expect. And this dark box, or this box is a dark box. It's also electromagnetically tight. So we actually did a test in which I put my phone in the box. People tried to call me and it didn't go through. So it is a Faraday cage. So that's kind of cool. And the translation stage is currently within the box. And this is the translation stage itself, which is composed of these 3 motors that we assemble together. And once these motors were assembled, then I wrote some different like shell scripts to actually run the translation stage and make it do different things. So the translation stage was assembled before the box was ready. So during that time period, I was trying to see how well the translation stage could be controlled. So we wrote the epic there, which you can see. This video is actually at 2 times speed though, just for your information. But yeah, I can write things very precisely. So you can see in this video. And so then part 3 of the actual process is the scanning, which unfortunately we didn't have time to do scanning with the strontium 90 source. But you can see this trigger tile holder up there that I designed in AutoCAD is going to have to be 3D printed in the future. There's also, this is the Janus software that we got running very recently, which will be part of the data collection. And then here is a video of the actual scan path with the laser, which will be what it will look like. The actual path will look like for the strontium 90 source scanning for about a 5 centimeter by 5 centimeter tile. And this video is also on 2 times speed. So it just goes kind of in a little bit like a zigzagging pattern. And then here, oh, and then it would collect data like at each point for the light intensity mapping. And so future plans are to take data with the silicon photomultiplier than just LEDs. Also to actually do the source testing in the box. And then like Alyssa spoke about, there are plans to kind of make a system with the translation stage and the suction cup, where suction cup or the translation stage will move, the suction cup will pick up the tiles, photos will be taken, and then those tiles will be able to be analyzed and characterized in that method. Yeah, so thank you for also to everyone in Rig, and does anyone have any questions?